Bismillahirrahmanirrahim. My name is Dr. Mukhtar Fatihu Hamza from Prince Sultan bin Abdul Aziz University here in Kingdom of Saudi Arabia. I'm happy to present my paper titled Genetic Algorithm-Based Autonomous Self-Localization and Mapping for Bomb Disposal Robots in this highly educative event. The outline for my presentation is going to be as follows: introduction, literature review, methodology, result and discussion, conclusion, and future work and recommendation, inshallah. This is my introduction. As we all know, in recent years, there has been an increase in number of attacks involving improved explosive device, that is IED. Civil unrest, wars, and political dispute are among the witness of such attack. Most frequently, the civilians and the military personnel become the target of these attacks. One of the popular methods of attack is by trapping IDE under vehicle. As you can see from this map, the attack of IED has been increased over the years for the past years, especially during 2012 and thereabout, especially here in Middle East. So basically, currently there are two prominent methods of detecting this kind of bomb. Normally, security personnel use mirror method and K9 unit, where they use police dog. The dog is well trained to sense and view foreign or any object that is suspected to be bomb. Also, mirror is used, and this mirror has been improved to a digital periscope, where a very sophisticated camera is used together with a video, where a security personnel can use it, and he can see the undercarriage of the car. Anywhere any foreign something is object is placed, the security personnel can see using this. Nevertheless, most of the bomb search still rely on manual inspection or this K9 inspection due to the ease of operation. This indirectly increases the risks to the security personnel, because the security personnel must be there, and these people who put the trap of the bomb, they are watching. If they see their secrets is going to be released, they can easily, it is time bomb, they can easily activate it. So the use of an automated system to navigate and search for foreign objects can help to reduce this risk. This is the motivation of this paper. In this paper, a simulation of robot navigation for vehicle and carriage inspection can be provided the initial feasibility of study for such system by observing the simulated navigation and searching behavior. Now, literature review. We have two literature reviews. One is bomb detection method. There are many types of bomb detection method. These are the most popular one: AUVIS, Intelscat Talos Plus, FIDO FXT, mirror method, K9, and bomb inspection robots. And this we compare them based on undercarriage view, sensing method, the risks to the security personnel, autonomous, and mobility. These are the comparison we made. Then secondly, we look at the path planning. You know, even in our work, the path planning is very, very important, and there are many methods that you can use to make the path plan where the robot will navigate undercarriage of the car. These are some of the method, that is, there's grid method, brute force, historic, A asterisk, greedy method, genetic algorithm, and anti algorithm. This anti algorithm and the genetic algorithm are part of the meta-heuristic algorithm, where you can use them for path planning. And these are comparison we made in terms of the optimization, in terms of the speed, in terms of the implementation. Some of them are simple to implement, and some of them are complex. Some of them are even very complex. But in terms of optimization, you can see the complex one, that is genetic algorithm and Connolly algorithm, they have global optimization, which means the path will be the best path that the robot can follow. Next is methodology. In this methodology, we are going to look at preparing vehicle environment, constructing perimeter, and undercarriage mapping. First of all, we have to look at the robot concept. The robot concept, the one we consider here, the proposed concept of the robot is shown in this big figure. The robot structure is chosen for its simplicity and ease of navigating. The robot has array of distance sensor on the top and side of the robot, as we indicated with this red and black colors. These sensors are used to detect collision and to scan the undercarriage of vehicle. The sensor on top of the robot are also used for perimeter, following similar pattern of the line following robot. The size of the robot, as we show in this table, the width is 20, robot length is 20, and the robot speed is 0.01 meter per second. That is the robot we are considering in terms of the concepts. Regarding the preparing vehicle environment, this can be summarized into few steps. That is image processing, vertical sensor feedback simulation, and lateral sensor feedback simulation. The simple image processing basically involves some processing of image to provide the input for the vertical sensor feedback simulation. The lateral sensor feedback simulation involves the simulation of sensor located at the side of the robot used to detect the wheel of the car. Then after this, we take undercarriage, the undercarriage image, which is then converted into gray scale image with the tires removed, as shown in this figure. The reason to convert the original image into grayscale is to simulate such that only one spectrum of the tone is considered instead of considering red, green, and blue. This image will be used to vertical sensor feedback. Then the sensor is imported to the MATLAB in form of matrix through the mread command, as we show in this table. So the image will convert into this matrix. Now, then we look at localization, navigation, and construction parameter map. Here, robot rely on edge of the vehicle to keep itself within the vehicle parameter. In order to achieve this, the robot use the distance sensor located on top and side of the robot to determine the position of the robot relative to the edge of the vehicle, as shown in this figure. This figure shows the possible position of the robot relative to the side of the vehicle. Robot can be left biased, centered, or right biased. All these positions will give different sensor values, which are used by the robot to determine the position of itself relative to the vehicle. Just like as this, when it is centered, it is assumed 0 for left bias, +1 for right bias, -1. The same thing for top bias, centered and the bottom when the robot is near the bumper of the car. So this too will help the robot to localize to know its actual location within the undercarriage of the car. And also during the navigation of the perimeter, the robot will need to avoid the tires. This is when the side sensor array are used to determine the collision as occur, as we show in this picture, where the robot can avoid touching the tire of the car. It means the robot can remain within the undercarriage of the car and will never collide with the tires of the car and will never come out based on this scenario. The local coordination can be like this. Let's assume that this was 0, 0 coordination is center. Then when it goes to the left, you can see some examples I give. Here it goes x -1, y1. Now this one x0, y5. The other one we even consider x to be 2, y to be 2.5. This one x to be 2, y 0.5, something like that. So this is the one that is used to map the location of the robot. Also, perimeter generated by the navigation. When we assume this is a perimeter navigation by the robot, you can see this pulse you see under it is where the tires are, and here is the front of the car, the back of the car, and this is the center. So these are the locations that the robot can navigate through. As seen in this perimeter map, some of the perimeter points are not continuous due to the only one axis is recorded during the navigation, like this. However, this can be mitigated by processing the perimeter map and fill the continuous point with interpolated coordinate or using previous coordinate of the missing axis. Just like this, you can see all these points now has been corrected. In order for this map to be useful for navigation, the map must be filled to high region within the perimeter to that robot only search for the thread within the region of the perimeter as this one. So now it has been filled already. This is the result of undercarriage mapping. We got that this is measuring, the first one A is measuring width and the second one B is measuring length, and you can see the intersection. That is where the robot is now. Next is result and discussion. The time taken to navigate parameter at 1 millimeter per second is presented in this table. You can see the time depend on the how large is the car. We use three cars, sedan, compact, and the pickup. So you can see the time. Also, the time elapsed and the distance of path planning method for different number of spots is presented in this table. And this is our result of simulated time elapsed, and this is the result of simulated distance. The performance distance in meter, we compare the gray, GA and GA based gray, and these are the results we got. Also, these are the results we compare for the paths generated for greedy GA and greedy GA based. In the conclusion, all the objective of the project has been achieved, and for future work, we can use now, instead of using only DA, we can use Connolly algorithm, and also we can introduce obstacle avoidance. Thank you very much.